Today we are walking through the paper titled Just Talk Minus, an agent that Meta learns on devolves in the wild.
Can we start with the big picture of what this paper is trying to do?
The paper asks how a deployed LLM agent can keep serving users without interruption and still get better as the task distribution changes. Its answer is MetaClaw, a system that improves two things at once: the model weights and the reusable library of behavioral skills.
What exactly was broken in the earlier approaches?
The paper points to three concrete problems. Some systems log raw trajectories but never distill them into reusable behavior. Others keep a static skill library that never feeds back into weight updates. And if you retrain the policy directly, you usually have to accept downtime, which is the opposite of what a live assistant needs.
So what is the paper's main move to fix that?
MetaClaw splits adaptation into two loops. A fast loop turns fresh failures into prompt-level skills that can be injected immediately with zero downtime. A slower loop waits for idle windows, then updates the policy weights with reinforcement learning so the agent gets better at end-to-end execution.
Before we get to the figures, what is the meta model they keep improving?
The paper writes the deployed agent as a metamodel with two parts: the base policy theta and the skill library S.
For this equation, what changes fast and what changes slow?
S is the fast-changing side because the system can inject a new skill into the prompt as soon as it distills one from a failure. Theta is the slow-changing side because weight updates are deferred to ARL training windows. That split is the core design decision of the paper. Now let us put the method overview on the board.
On this overview, what does the left loop do that the right loop cannot?
The left loop is the zero downtime path. It reads failure trajectories, asks an LLM evolver to write a new reusable instruction, and applies that instruction on the next task without touching the weights. The right loop cannot react that quickly, but it is what actually improves the policy itself. It waits for safe idle windows and then trains with cloud lower ion day, or else the agent can execute more reliably.
What keeps the training data from getting mixed up after a skill update?
The paper handles that with skill generations. Failed trajectories in the support set are used to make the next skill library, and only trajectories collected after that new library is active are allowed into the ARL buffer.
So the key is that the new skill library is applied first, and the weight update only trains on behavior collected after that?
Exactly. The paper calls the old failure data support data, and the later post-adaptation trajectories query data. When the generation counter advances, stale samples are flushed, so ARL optimizes the adapted agent instead of rewarding behavior from an outdated skill set. With the mechanism in place, we can move to the first key result figure.
Where is the advantage most obvious on this chart?
The biggest separation is in the middle of the schedule, around days 11 through 22. That is where tasks require multi-step procedural compliance, so distilled skills are most useful. And the full system reaches nearly a 0.8 accuracy advantage around day 19 or 20. Early days are simple enough that most systems already do fine, and late days are so hard that everyone starts collapsing together. The next result figure shows why the two adaptation loops matter for different kinds of tasks.
What does this chart say about skills alone versus the full pipeline?
It shows a clean division of labor. Skills alone help reasoning-oriented tasks, so multi-house improves when new instructions are injected. But file-check tasks stay flat until the policy itself is updated. Once the full pipeline runs, Kimike the 0.5 spot I completion jumps from 2.0% to 16.5%. And on part I file check completion rises from 18.2% to 51.9%. So prompt skills help the agent know what to do, while weight updates help it carry the whole procedure through without breaking.
So how large are the gains once both mechanisms are running together?
For the weaker base model, the improvement is large. On MetaClaw bench part I, Kimike to 0.5 goes from 21.4% accuracy to 28.3% with skills only, and then to 40.6% with the full pipeline, nearly matching the 41.1% baseline of GPT 5.2. The paper also reports up to 32.2% relative gains from skill-driven adaptation alone, which shows that the fast loop is already doing meaningful work before any ARL update happens.
Does the idea still help outside this benchmark?
Yes. On Auto Research Core, which is a 23-stage autonomous research pipeline, skill injection alone improves the composite robustness score by 18.3%, cuts refined cycles by 40%, and raises pipeline completion from 18 of 19 stages to 19 of 19. That matters because those gains appear without any gradient update at all.
What do the case studies add beyond the aggregate scores?
They show that the two mechanisms fix different failure modes. In one case, a single distilled skill resolves a compliance error with no weight update at all. In another, the skill gives the right formatted context, but the agent still needs weight level ARL updates to execute a structurally harder file operation reliably. So the paper is not claiming that one mechanism replaces the other. It is claiming that each one covers a different weakness.
What should we treat as the main KDR?
The paper is careful about that. MetaClaw bench is an authored simulation rather than raw production traffic, so the exact numbers should not be read as guaranteed deployment gains. The day-by-day plot also shows that very hard late tasks still defeat every system, and the idle window scheduler depends on user configuration and environment signals, so that part may not transfer cleanly everywhere.
So the real claim is that a deployed agent can keep serving users while also getting better at adapting over time.
That is exactly the point. Humped-level skills give MetaClaw immediate zero downtime adaptation. Wait updates recover reliable end-to-end execution. And together, they let the agent improve while it is already in use. That is why the paper frames MetaClaw as an agent that learns and evolves in the wild. That wraps up this paper workflow.